So this video, I'm assuming y'all have watched videos 1 to 6, and these are just some extra topics that you may or may not need for your calculus exam, so feel free to look at these. So first one we're going to be covering is inverse of 3 by 3 matrix, then parametric equation of a line, which is going to be useful for finding out the intersection of a line and a plane. Then we're going to find out the distance, the shortest distance from a point to a plane, the shortest distance from two parallel planes, so the distance between two parallel planes, and then three variable system linear equations. So once again, I'm assuming y'all are familiar with the concepts in videos 1 to 6 because these ideas are just applications of what you can do with the knowledge that you have gained in those videos. So for finding inverse matrices, it's the exact same formula. If I have some, let's say if I'm trying to find A inverse, that's just going to be equal to 1 over the determinant of A. And then that's going to be multiplied by the adjacent of A. So we know how to compute the determinant of 3 by 3 matrices, but it's this adjacent part that's a little new, and we're going to have to learn a new method for calculating that. There's actually two ways to do this, two main ways. So I'm going to be showing you both ways, and you're going to see that we arrive at the same answer. First, let's compute the determinant of A, or in this case, D. So what is the determinant of D? And by the way, shout out to Khan Academy for providing these types of questions. So what is the determinant of D? Well, that's going to be 0 multiplied by whatever the determinant of this small matrix is. That's just going to be 0. And it's going to be minus 2 times the determinant of, well, look at 2 right over here. It's in the first row and second column. So the remaining numbers is 0, 2, 1, 0. So it's going to be the determinant of this small matrix 0, 2, 1, 0. And I'm just going to do the calculations really quickly. So 0 times 0 is just 0. And then that's minus 1 times 2. That's negative 2. And finally, plus, and then you're going to move over to the 2 right over here. And you see that's in the first row, third column. So that's the resulting matrix. So the determinant of this, well, that's 0 times 2, which is 0. And that's going to be minus 2 times 2. That's negative 4. This is ultimately going to be 2 multiplied by the negative 4 that we get from here. Let's see. That's going to be 4 minus 8. That's negative 4. So let's save that. Now we have to find out the adjacent of A. And let me tell you something. This is something that I really don't like doing because it's just a very like tedious process. It's very easy to get things wrong when you're trying to compute the adjacent of A. So here are the steps. The first thing you want to do is you want to find the matrix of minors. So that's what it's called. Step 2 is you want to find the cofactor matrix. And then step 3 is you transpose that to get your inverse matrix. Or after you multiplied everything by 1 over the determinant, you have your adjacent. So that after you transpose it, you get your adjacent. Then you multiply by 1 over the determinant, and then you get your inverse. So let's start off by doing this. What is the matrix of minors? So you know how for the determinant of a matrix, you kind of have to do this tedious process where you cover up the row and the column that the number's in, and you calculate the resulting determinant right here. And then you have to do it for, everything right over here, everything right over here, right? That's the process that we used. And we just have to do that process for every other number now. So if I write out this matrix, let's actually find out the matrix of minors first. So I'm going to move this. So let's say we have 0, 2, 2, 0, 2, 1, 2, 2, 0. And we're going to write out this big matrix here. So imagine if you're at this point 0. First row, first column. This is the resulting matrix, 2, 1, 2, 0, and the determinant of that will be the first thing right over here. If you're in first row, second column, so this 2 right over here, the resulting matrix is 0, 1, 2, 0. And I hope you can kind of see where I'm getting with this. If you're in this right over here, if you're in the first row, third column, that's your resulting matrix, and you can see the trend, right? If I'm in the second row, first column, 2, 2, 2, 0, that's my resulting matrix. And you literally just do that for every single space that you have in your, or every single number that you have in your matrix, right? You kind of do the cover up method, I guess you can say, and the resulting matrix that you get, 0, 2, 2, 0. That's going to be what makes up the matrix of minors. So I'm probably gonna do a time lapse here of me just doing this. So there we have it. And now we just have to compute all of these determinants. Now that we found a matrix of minors, it's time for step 2. You find the cofactor matrix. Cofactor matrix is actually very easy. What you have to do is you apply a checkerboard pattern to all of these spots. So depending on your position, you're going to get multiplied, or you're going to get multiplied by either a positive or a negative. So in this case, right, if I have -2, notice how it's in the positive position, which means that it just remains unchanged, right? Because -2 times, you can think about these as invisible ones. So -2 times +1 is going to give me -2. But then the position where you have the negative signs, you're just going to flip it. So for example, notice how -2 in this checkerboard pattern right over here, it corresponds to this negative sign here. And so what you're actually going to do is you multiply those corresponding spots where the negative signs are. So I'm just highlighting it over here. And you multiply those corresponding spots just by -1. So you just flip the sign. So -2 becomes +2. So do these two, and then the sign of 0 doesn't change. Finally, you have to do something called transposing a matrix. That's another operation that, I mean, if you're taking linear algebra, you got to be familiar with. Transposing pretty much just means that you, in a way, you flip a matrix. So what transposing a matrix looks like is you're just flipping the rows into columns. So for example, the first row of this matrix becomes the first column of your transposed matrix. So this is -2, +2, and -4. The second row of your matrix becomes the second column of the transposed matrix. So this is going to be +4, -4, +4. And finally, third row, you know the drill, third column. There we have it. This is going to be equal to the adjacent of our matrix D. And so if we put everything together, well, we have 1 over the determinant, so that's going to be 1 over 4. So let's actually compute the inverse matrix now. So this is going to be 1 over 4, -4, multiplied by, this entire matrix, right? So we're just going to multiply everything in this matrix by 1 over -4. So we're going to get 1/2, -1, 1/2, negative 1/2, 1, 0, 1, negative 1, 0, and there we go. This is going to be equal to our inverse matrix. Okay? Okay? So this is just the three-step method for finding out the determinant of, or sorry, the adjacent of a matrix. Now, if you just want one method, you don't want to do like all these determinants. You just want to do one goal that you can reach to get the inverse matrix. And what I mean by that is there's actually another way to get the inverse matrix, and it's actually by doing something pretty cool. So instead of doing all those steps, you just have one single step, but it takes a little long depending on the matrix you're dealing with. But nevertheless, it's one step. And what you're going to do is you're going to set up your regular old matrix on one side, and you're going to set up the identity matrix and separate it by this little bar. So your job now is to use Gaussian elimination, and you want to try to get the left-hand side looking like the inverse, or sorry, the identity matrix. So you want this side to look like the identity matrix. All right, and whatever matrix that's resulting on the right side is going to be your inverse. So let's see how we can get this side into the identity matrix. So I guess I can swap out. So I guess I can swap this row right over here and place it to the top. So I'm gonna get, you can imagine that I'm just gonna bring everything. I'm just gonna bring this row to the top. All right. Okay. What else can I do? What if I subtract this row right over here by this row? If I subtract those two, well, that means I'm going to get 0 here. So I'm going to get 0 minus 0 is 0. I'm going to get 2 minus 2, which is 0, and 2 minus 1, which is here. And then on the other side, I'm going to get 1 minus 0, which is that, and 0 minus 1, which is negative 1, and a 0 there. So let's actually put this, because we want everything in like the identity matrix form. Let's put this at the bottom. All right, so that we're able to get this diagonal of 1s, right? That's our goal. What else can we do? I guess we can divide the second row by 2, or multiply it by 1/2, right? So if I multiply this by 1/2, this is just 1, 1, 1/2. 1, 1, 1/2. And now if I subtract these two rows, I'm going to get negative 1/2 here. That's going to be positive 1. And then on this side, you're just going to get 0, 1, 0. So let's put that in. And right up here. Just going to put that here. Okay. The final thing I really have to worry about is this top row. Once again, I guess I can start out by dividing this by 2, or multiplying by 1/2 once again. So this just becomes 1, 1, 1/2. And then I can subtract row 1 by row 2. So I get 1 minus 0 is 1. This is 0. 0 minus 0 is 0. And then 0 minus 1/2 is positive 1/2. 0 minus 1 is negative 1. And 1/2 minus 0 is 1/2. So I'm just going to replace this entire thing with this, right? And then I'm just going to replace this row with this, right? This is our resulting matrix. Notice how on our left-hand side, we've transformed our original matrix into the identity matrix. We transformed it into the identity matrix, meaning that on our right-hand side, this has to be the inverse. So this is actually your answer. And guess what? It matches up with what we have right over here, the other method that we did. So this method is good if you don't want to go through the complications of calculating the adjacent and the determinant, and you're good with like manipulating systems of linear equations, but you still get the same answer at the end of the day. So choose whatever method you want. Now, the reason this works, well, it actually goes into a little bit of linear algebra. But keep in mind that A inverse, right, of A, that gives you the identity matrix. And this idea pretty much is what we're doing here. All right, so just know that this basically connects to this, but not a full explanation because this is multivariable calculus and not really a linear algebra course, even though there is some linear. So here we're going to explore parametric equation of a line. So a parametric equation of a line, you're going to recognize the fact. So the big idea is that it pretty much stems from y is equal to mx plus b, because at the end of the day, it's just a line. Okay. So usually you would like to use parametric equations if you have a function, let's call this r, and which we know that basically represents the position of your particle or whatever you're trying to model. So this is the position, and that's going to be equal to, I'm just going to call this r of 0. So we're going to be given an initial point. So r of 0 it's just a point. You can think about it as like our y-intercept if you want to relate it back to y is equal to mx plus b. And this is going to be equal to, this is the initial point plus some vector, which I'm just going to call vector v, multiplied by time. So this vector v right over here pretty much represents the slope of our function. It's going to represent how much our x increases, how much does our y value increase, and how much does our z value increase as our particle moves throughout time. So this velocity right over here, it's pretty much our slope. So let's look at an example. But actually, one more thing before we start. It's also important to know that r of t, we know that it represents the position of the particle that we're trying to model, right? So I'm going to put the slope up here. So pretty much the general form of r of t that we saw in previous videos, that's going to be your x position is going to be changing over time. So it's some function of x, comma, some function of y of t, right? And then some function of z, right? Z of t. Okay. So we're going to see how we're able to convert from these specific parametric equations, right? So the parametric equation for each component, and we're going to see how we can convert it into like the specific form of it. So let's say that we have a point. Let's call this R0. Let's make this easy. Now let's say that this point is currently at 1, 2, 2. Okay. And let's say that the direction vector, so I'm going to say that my vector right over here, let's say that's going to be equal to 2, 3, 4. And this vector right over here, this has to be a vector that's parallel to our line. Think about it. Let's make this simple, and let's say that we have our coordinate, right, x-axis, and we have the y-axis here. Let's say we're given our initial point, right, which we can think about, this is going to be r sub 0. And then we're going to be given a vector, right, that's going to be parallel to this line. So this is going to be vector v. So you can imagine that this line right over here is pretty much going to be parallel to this vector v, right? And in fact, the vector v is going to represent, in this case, the change in x, right? How much does x change as our time increases by 1 unit? And it's also going to represent how much our y value increases, so the change in y as time increases by some amount. And if we're dealing with 3 dimensions, which we are in this case, it also represents how much does our z value change as time passes. So one way to interpret this vector is that our change in x over time, right? If we increase t by 1 unit, our x value will increase by 2 units. For our y velocity, right, if we increase our t value by 1 unit, well, our y value is going to increase by 3 units. And for our z value, well, if we increase time by 1 second or 1 unit, whatever we're dealing with, our z value increases by 4 units. So this is just the velocity, that's just a special way of saying like slope. After all, velocity is change in position, so it's just the slope of our line. Okay, so now we're able to write out our equation, right? This is r of t. That's going to be equal to our initial point, and then plus our velocity vector, and then multiplied by time. And then if we, simplify things a little bit, I get that r of t, and that's going to be equal to 1 plus 2t, and that looks like 2 plus 3t, and then that's going to be 2 plus 4t. Okay? And so if we actually, it turns out that this is like the general form for, the position of your particle. But if we want to convert it into like the more general form where we're given x of t, y of t, and z of t, right, pretty much explicitly, well, we're able to simplify this, and we get that the corresponding x of t is going to be equal to our initial x value plus essentially the change in x, y of t, initial y value plus change in y, z of t is initial z value plus change in z. It's all literally just stemming from the fact that y equals mx plus b when you're dealing for a line, except this time controls change in x direction, the change in y direction, and the change in z direction. So there's going to be 3 equations, but the concept is still there. Okay, so for practice, r of 0 is equal to 3, -2, -5, and let's say that our vector that's parallel to the r line, let's say that's equal to -2, -5, and 7. So for practice, I want you to find out the explicit form of r of t. So everything's simplified, and I want you to identify x of t, y of t, and z of t. Okay? Now, more formally, so that's just going to be practice for y'all. So more formally, x of t, a lot of times you may see it defined as the initial x value, so x sub 0 plus, I can say that our velocity in the x direction, I can just call that a t, y of t. That's going to be equal to our initial y value plus bt. And then z of t is going to be equal to initial z value plus ct, where x sub 0, y sub 0, z sub 0 makes up our x sub 0, y sub 0, z sub 0 makes up our initial point, so I can just call that r sub 0, and a, b, c, that's just the slopes in all the directions, which defines our velocity vector. So that defines the velocity vector. So if you really like formulas, well, this is for y'all. But the most important thing to note is that this is just y is equal to mx plus b at the end of the day. Okay? The velocity vector, you can think about it as it's broken up into components, and each component describes a separate change in some axis direction. So why is this important? Well, this goes into this topic, which is, imagine if you have a line that's intersecting a plane, and you want to find that intersection point. The way you do that is, well, first recall what the equation of a plane is. Ax plus by plus cz, that's going to be equal to d. Now, our line can be expressed as the parametric equation. So I can say that r of t is equal to, we said how that's equal to x of t, y of t, and z of t, right? So another way to say it is that x of t is equal to our initial value plus at, and then y of t is equal to our initial value, blah, 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 right? But the point is that we're able to plug in the relationship between x and t into our plane equation, right? So wherever we see an x in our plane equation, we replace it with this parametric form, right? wherever we see y, we replace it with its parametric form. And wherever we see z, we also replace it with its parametric form, so that everything is in terms of time. So through this way, we're able to solve for the t value, because this just becomes an equation where our only unknown variable is the t value, and then we just evaluate the x, y, z value at that specific time moment. Okay, so let me give you an example of that. So this is just a simple example. So we have x of t is equal to 1 plus t, y of t is equal to 2 minus t, and z of t is equal to 3t. So we're just able to substitute in all of these values to the equation of the plane. And then after that, we're able to solve for the time value that makes this true. So what do we get? This is 2 times 2 plus 2 times t is 2t. And we know that y is 2 minus t. This is going to be plus 2 minus t minus 3t. That's going to be equal to 5. So what do we have here? That cancels out to be minus 2t. That cancels out to be just 4, right? So 5 minus 4 is 1. I can say that t is going to be equal to negative 1/2. Okay? Now what do we do after this? After we get t is equal to 1/2, we just have to substitute everything back into our xyz equation. Because at the end of the day, right, we have a position function, right? We have r of t that describes the position of our particle on the line at any moment, right? So if we have a line and a plane, right, r of t pretty much describes any point on this line. So we found out that this line and this plane intersect at the time value t is equal to negative 1/2. So we just have to evaluate r of t at t is equal to negative 1/2. And then we get the position at that specific point. So when we plug in 1/2 into that, we get x value of 1/2. Let's see, that's going to be 2 and 1/2. And then that's going to be negative 3/2. All right, let's just write this as 5/2. And there we have it. That is going to be our answer. So you see how for finding out the equation of intersection of line and plane, right, all you have to do is you have to find out the parametric equation for the lines. And once you do that, then it's just substituting into the plane equation and then solving for that time variable. Now, if you get a scenario where the time variable cancels out, so you're left with some constant, let's say 4 is equal to 5. All right, and let's actually do an example to show you what I mean. So let's say that when we're able to plug everything into our equation of the plane, we get a scenario where all the times cancel out, and we're left off with something that's not true. So let's say we have something like this. Let's substitute everything in. So we have 2 plus 3t plus 2 minus 2t minus t is equal to 10. Okay. Now, when you simplify everything, well, the t's all cancel out, so you're just going to be left with 4 is equal to 10. And what this tells you is that you're going to have a plane, but then you're going to have a line that's parallel to the plane. So you end up with no solution. Okay? So when the variable t cancels out, and we're left with something that's just not true, then there is no value of t that satisfies this equation, so these two things must be parallel. Let's look at the final scenario. What if, instead of ending off with a false statement, what if we end up with a statement like 10 is equal to 10? Let's look at an example of that. What if we're given an equation like this? Let's substitute everything in. So we get 3 plus 3t plus 2 minus 3t minus t is going to be equal to 5. Right? Did I do this correctly? That's going to be minus t. Okay. Did this a little incorrectly? Let's pretend that this is a 2. All right. I'm just gonna put this in another color to highlight this. My bad. But notice how once I changed this to 2t, right? Notice how this 3t minus 2t minus t, it all cancels out. So I'm just going to be left with 3 plus 2 is equal to 5, and indeed, 5 is equal to 5. What this means is that if you have a graph, right, and you model out the plane, so this is the plane, what you're going to end up finding out is that the line is going to be inside the plane. It's going to be on the plane. So every value of t, no matter what value of t that you choose, the line is always going to be intersecting the plane, which means that it's just on the plane. Say that I have a plane written in this equation, ax plus by plus cz plus d is equal to 0. And let's say if I'm given a point P1, let's say it has the coordinates x1, y1, and z1. I want to find out the shortest distance from a point to a plane. So how am I able to do this? Well, one thing that's really important, you might recall this, but if you have a point and you want to find out the shortest distance from it to a line, well, notice how the shortest distance is always going to be perpendicular, right? It's always going to be perpendicular to this line. Think about it. Think about any other scenario. Let's say if this line was a little bit slanted, right? It wasn't a perpendicular distance. Well, that wouldn't be the longest distance, because notice how I can make a right triangle, and so this side is the hypotenuse, while this line that's perpendicular to this line that I have here, that's going to be a shorter distance than the hypotenuse. So all in all, what I'm trying to get at here is that the shortest distance from a point to a plane, well, that distance is going to be some line, some vector that's going to be perpendicular to the plane. All right, and then we're just going to take the magnitude of that vector to find a scalar quantity, to find the distance. Okay, so whatever we have going on here, whatever distance that this is, which I'll call, let's say, d, right? Whatever d is, right? As a vector, this has to be perpendicular to the plane, and we're just going to have to take the absolute value of whatever this vector is to find out the displacement. Now, let's say if I have another point, p0, p sub 0, and let's say it has the coordinates x, comma, y, comma, z. Now, p sub 0 is very nice because it represents a point. It can be any point that's on this plane. Okay, so let me just draw a vector from p1 to p0. So I guess I kind of have the numbers backwards, but it's fine. Let's just continue with this. So this vector p1, p0, well, what is this going to be equal to? Well, p1, p0, that's just going to be all the components of p0 minus the components of p1, respectively. So this is going to be x minus x1, comma, y minus y1, and then comma, z, comma, z1, or z minus z1. Okay, this is pretty cool now. So we have this vector p1 to p0, and we're trying to find out this distance right over here. And we know that this distance, or this vector that I have right over here, whatever this vector is, it's going to be perpendicular to my plane. Well, what's another vector that's perpendicular to a plane? It's in the definition of a plane. It's the normal vector, right? Recall that the normal vector is composed of a, comma, b, comma, c, right? Those are its components. Because the definition of a plane, or at least one of its definitions, is that it has a normal vector, and that defines the orientation of the plane, and you also have another point on the plane that determines where the plane is. All right? So we're going to use this definition to help us out. So I have this vector here, and I have this normal vector. So how can I find this distance? So how can I get d? Well, remember your fancy linear algebra operations. If I take the projection of this vector onto the normal vector, then what do I get? Right? So imagine if this was the I'm actually going to draw here. Imagine if this was the normal vector, and then this is the vector from P1 to P0. The projection of this vector onto this vector, well, that's just going to give us, right? So this vector onto this vector, that's just going to give us this distance right over here. And guess what? Or actually not the projection, but the component of, so if this is the component of P1, P0 onto the normal vector, right? If we take the component of P1, P0 onto the normal vector, then that's going to be equal to our displacement, right? Or the distance from the origin. So we're able to use these fancy linear algebra operations to help us solve this problem. Now recall the formula, all right? So the component of u along v is going to be equal to u dot v divided by the magnitude of v. So in this case, we're going to do the same thing, except this time we're just going to take the dot product between here, p1, p0, dot the normal vector, divided by the magnitude of the normal vector. Okay? Now here's where things get a little bit tricky, because a dot product could be negative, but if we're dealing with a distance from the origin, we want that to be always positive. So we're actually going to take the absolute value of the dot product, and that way we're going to get a positive value, okay? Now let's just simplify things a bit. So we know that this is P1, P0, and we know that this is n, right, our normal vector. So let's write everything out in terms of components. So first off, what is the magnitude of n? Well, you might recall the magnitude of the vector is just the square root of all of its components squared. So that's the square root of a squared plus b squared plus c squared. Okay, that's good. What about the top? Well, the dot product between these two vectors, well, let's just multiply everything out and see what happens. So you have a times x minus x1. So that's a times x minus x1. And then b times y minus y1, y minus y1, and then c times z minus z1. And we're actually able to group those terms together. So if we actually expand everything out and then we group all the terms together, we actually get this, okay? Now, what is ax plus by plus cz? Well, that stems from the equation from our plane. And if we move the d to the other side, we get ax plus by plus cz is equal to negative d. So this is equal to negative d. Meaning that we can actually use this equation right over here and substitute negative d in for ax plus by plus cz. So let's actually do that. So we get negative d. Okay, we can factor out a -1 from everything. And once we factor out the -1 from everything, then that's just the magnitude of -1 times the positive sum of these terms. And so ultimately, what we get is d plus ax1 plus by1 and then plus cz1. Okay? And in fact, let me just move the d to the back. It's still positive. And so this is the formula that you've probably seen like your textbook or maybe some other video. Well, that's how you get the formula. This is going to be the absolute value of ax1 plus by1 plus cz1 plus d, all divided by the square root of a squared plus b squared plus c squared. Okay? Now, think about it, right? If x1, y1, and z1, if they were really, really far away from our plane, right? Let's say if our point P1 was all the way up here. Then notice how if we plug in x1, y1, and z1, we would get a much larger magnitude on the numerator. And that signals that we are further away from our plane. All right? And likewise, if the equation of our plane, right, we also said how d kind of represents the distance of our plane from the origin, right? It's proportional to that value. So if I pull up Desmos here, I pull up a 3D graph. Let's say if I have x plus 2y plus 2z is equal to 1. Actually, let's move this 1 to this side. right? If I increase this value, okay, so I have pulled up Desmos now, and I've just moved this d term to the other side. But notice how as I increase d, it's further and further away from the origin, right? As I increase the value of d, it gets further away from the origin. In fact, because this is Desmos Notebook, I can do something really cool. I can add a slider, so I can create a slider for a, and I can set this equal to a. So you can see that as I increase my value, our plane is moving further away from the origin. So if this value of d is large, well, our plane is probably going to be further away from the origin, so this entire plane is going to be like right over here, and therefore there's going to be a greater distance to the point that we're focusing on. Let's say that we're going to apply this formula to finding out the distance between two planes. So let's say if we choose an arbitrary point on our first plane, all right, so any point on the first plane, let's call this x1, y1, z1, all right? So this is the equation for our first plane. The equation for the parallel plane is this. And notice how the only thing that's different about these two planes is that d value. Why? Well, take a look. Notice how these two planes are parallel because the normal vector to the two planes defines their orientation, and they have the same normal vector. The only thing that differs is that d value, which you can toggle on, right? You can toggle it up and down, and it basically defines the distance from the origin, or how far away it is from the origin. All right. Now, it's important to note that when we're using the equation for a point-to-plane distance, so what I'm going to do now is, right, given a point on the first plane, I'm going to find the shortest distance from the first point, right, to this plane right over here, right? And once I get this distance, well, that's going to be the shortest distance from plane 1 to plane 2. So that's going to give us the distance between the two planes. So I'm just going to apply this formula to this scenario here. So what are we going to get? Well, we're actually going to get pretty much the exact same formula we have here. Because notice how the normal vector, notice how our normal vector is still a comma b comma c, right, from the coefficients of our equation. So we still have that a squared plus b squared plus c squared, and we're still going to have all of this. But this time, we're looking at the distance from plane 1 to plane 2. So instead of this d plane right over here, because before we were examining a point and a plane, so this is the d value of the plane that we were examining. Now we're examining the d value of our second plane. So we have to be specific here, right? This is going to be the d value of our second plane because we chosen a point from our first plane and we want to find a distance to the second plane. All right, so I'm going to say this is plane number 1, this is plane number 2. And we're finding the distance from 1 to 2. All right, so that's why I have a 2 here. Now, notice how ax1 b plus by1 plus cz1, well, that corresponds to the equation, this part of the equation for my first plane. And notice how that's just equal to negative d1, right? So I can substitute that in right over here. And the reason why that works is because recall that x1, y1, z1, that's we could have chosen any point on our first plane, right? We could have chosen any point. x1, y1, z1, that represents any point on the first plane, all right? So because that point corresponds to the first plane, these coefficients, they also correspond to the first plane. So instead of ax blah, 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 I'm just going to get the absolute value of minus d1 plus d2 all over a squared, the square root of a squared, b squared, c squared, and too lazy to write it down. But the thing is that you can swap, you can multiply this by -1 essentially, and you get d1 minus d2 because absolute value properties, right? This is still going to be equal, and we're going to have the divided by a squared plus b squared plus c squared on the denominator. All right. So what this formula is saying is that if we take the distance between the d values and we divide it by the square root of a squared plus b squared plus c squared, that's going to give us the distance between the two planes. And it makes sense that the distance of the d values are included in the formula. After all, that's the only difference that we have between the two planes, right? That's what defines how far away the planes are, right, in the first place. So we're able to apply these components, right? The idea of component of U onto V, and we're able to solve a seemingly pretty tricky problem. Quick 1-minute topic. Let's say that you want to find out the angle between two planes, right? So this is plane 1, and this is plane 2. You want to find out the angle between them. Well, that angle is just going to be equal to the angle of the normal vectors, right? So if I draw a normal vector here and draw a normal vector for the second plane, right? This angle of the two planes, between the two planes, is equal to the angle between the two normal vectors, because after all, the normal vector is what defines the orientation for the plane, right? And the normal vector is just a 90-degree from the plane, and so it's going to have the same angle. So you find the two normal vectors, and to determine the angle, you just use the dot product, because you know A dot B is equal to magnitude of A times magnitude of B times cosine of theta, and there you have it. The final thing that I want to get into is system of linear equations with 3 variables. So let's say if I have x plus 3y plus z is equal to 2. And let's say if I have y plus 2z is equal to 3. And then I have x plus 3z equal to 5. How can I solve this system of linear equations? And one way to do it is you convert it into this fancy linear algebra form, where it's a matrix, and the matrix, and essentially the matrix contains the coefficients of all the x, the y, and the z terms, all lined up in a nicely organized way. So there's 3, 1, 0, 1, 2, 3, right? It just represents the coefficients. And you can imagine that if you multiply this, you matrix multiply this by x, y, and z, you're going to get 2, 3, 5. This is just our system of linear equations written in a fancy way, because if you recall matrix multiplication, well, 1 times x plus 3 times y plus 1 plus z is going to be our first item. Then we're going to have 0 times x plus 1 times y plus 2 plus z. That gives us our second equation, and you kind of see the pattern there. So it's all we maintained all the information, but we just compacted everything into like matrix form. Now think about what we're solving for. We're trying to solve for the x, y, and z values that makes all these equations true. And geometrically, what that represents is, well, the intersection between 3 planes. Because notice how this right over here, that's an equation of a plane, right? Ax plus by plus c, z plus d is equal to 0, or sometimes it's written with a d on the other side. But the point is that these are our planes. And so I can actually write them. Maybe I'll graph it out. So this is x plus 3y plus z is equal to 2. That's our first plane. Then we have y plus 2z is equal to 3. And then x plus 3z is equal to 5, right? So the intersection between the 3 planes, that's going to be the solution to the system of linear equations, right? And you notice how all of these planes intersect at this one point right over here. Let's find that point. And we can find it using the same method that we did in the beginning, Gaussian elimination. So it's pretty much the same thing that we did in the beginning of the video for doing the inverse matrix in the second way. We write out all of our numbers, and then we're going to put this bar over here, and then 2, 3, 5, and then we're going to try to manipulate everything so we get it into row echelon form. Now, I'm going to leave that as an exercise to y'all. So what you're able to do is what you usually associate with regular old system of linear equations. Like you're able to multiply an entire row by some number, which multiplies the entire row and the answer. You're able to subtract columns or subtract rows and add rows, all right? And specifically, row echelon form basically allows you to find out the value of all of your variables. All right, it's a form that makes everything very nice. Now you can get a variety of scenarios, and once again, I don't want to get into too deep into the linear algebra aspects of it, but you want a staircase pattern. So what I mean by that is, let's say if we have something like this, all right, and okay. And here's an example of something in row echelon form. And let's say that's equal to 2, 3, and 4. All right. Notice how this is basically saying that our z value, right? What is that equal to? Our z value is equal to, after you have everything into row echelon form, you're able to solve the system of linear equations. So what you want is this staircase pattern, all right? And what this translates to is the fact that, think about it, this is saying that 7z is equal to 4, right? This equation is saying that 5y plus 6z is equal to 3. And the top equation is saying that 2x plus 4y plus 5z is equal to 2. So notice how in this form, it's very easy to get all the solutions to your x, y, and z value, because you solve for z first, then plug in z in for this value, then solve for y, and then plug in both y and z into the last equation, and then you're able to solve for all the values. So that's pretty much your goal. Now, it turns out that this equation has one solution, all right? And that one solution is this point right over here, all right? I spoiled it. Now, as for the results of these system of linear equations for 3 variables, there can either be one solution infinitely or no solution. All right. So let's see if I can do this. If there's, well, these are the same plane, so they actually would have infinitely many solutions. So I guess this is one example where you just have like the exact same, plane, and therefore there's going to be infinitely many solutions, which you can think about as this line right over here. All right, so the solution to this system of linear equations is just going to be this line, right? Because that's where both the purple and the gray plane intersect with the green plane, right? Or there can be no solution, right? If I do something like this, now these two planes are parallel, they don't intersect. And if the parallel planes don't intersect, then these 3 planes together don't intersect at one point. So this system of linear equations is not going to have any solution as well. And there are other facts about these types of linear equations. For example, we could dive deeper into the determinant and seeing how the determinant is 0 or non-zero, what that means for system linear equations, but that's all I'm going to leave y'all with because the video is getting pretty long. All right, have a great day.